All that we've done so far has been talking about what we call direct current. Direct current only flows in one direction. If I drew you a graph of direct current, or the potential difference driving it, you would find that it looked something like this. It's always the same. It flows in one direction all the time. Now, direct current is brilliant. We get it from cells and batteries. We use it to run things like laptops. We use it to run torches and iPods, and anything that has a cell or battery in it will run on direct current. It's really useful. However, the mains electricity that we use is not direct current. One of the reasons for that is to do with how we make electricity, and it's a lot easier to make alternating current electricity. Now, alternating current, or AC, is a little bit different. If I draw a graph, potential difference or current for alternating current, you will find that it follows this kind of pattern, like a sine wave. Now, alternating current changes direction. It is constantly changing direction. That means that the electrons are flowing one way, then the other, one way, then the other. They are constantly changing direction. Now, that's perfectly useful. It still powers things. That's why we use it as mains electricity. It still does the job, but it's important to know that this current is constantly changing direction. There are a few other things you need to be aware of. That one wavelength, if you like, the time it takes for alternating current to do one cycle, that's go forwards, then backwards, at this point, we call that the time period T. And sometimes we'll talk about the frequency of an alternating current supply. And the frequency is how many of those do we fit in a second. And that's just 1 divided by T. That's the frequency. It's measured in hertz. And in Britain, our mains power supply runs at 50 hertz. That means that the electricity that you get from a plug socket changes direction 50 times every second. So your lights are actually flickering 50 times a second, which is far faster than your eyes can detect, but it is still happening. You also need to be aware that the voltage of the UK power supply is 230 volts. Different countries may have slightly different values, but in Britain we have 230 volts changing direction 50 times a second. And those are two key numbers that you need to be aware of. Now, when we're using mains electricity, you're all used to using a 3-pin plug. You know what they look like, you plug them into the socket regularly, and you expect them to always work. But a 3-pin plug has some really important features. First of all, it has a cable. Now, a cable is made of 3 wires, and those 3 wires are all separately insulated, but there's also this outer insulation. Now, that's just to keep you safe. That's to make sure that you cannot touch any of those live bits of cabling, of wiring that could do you harm. So we have that outer cable. Inside the plug, that cable will always be screwed down with this cable grip. Not the most imaginative name, but a really useful part of the plug that holds this cable in place. Notice it grips the outer insulation, and that guarantees that this cable is not going to be pulled out of the plug, which helps to keep you safe. Now, inside that cable, as I said, there are 3 wires, and they're all separately insulated. First of all, there is the live wire. Now, the live wire is normally brown, which is slightly confusing because that means that it looks dead, but we have this brown live wire, and at the end you might see a tiny bit of copper peeking out, but that will be screwed into a contact point. So there we have our live wire. It is always connected to a fuse. So live wire to a fuse. We'll talk about what the fuse does in a moment. After that, we should have a blue wire. And the blue wire is our neutral wire. And again, it's got copper inside it, inside that blue insulation, and it has its own pin that it's connected to. So there we have our blue neutral wire. Now, the way that AC works is that we'll say the potential difference of the live wire varies with respect to the neutral. So we imagine that the neutral wire stays perfectly at 0, and the live wire changes from positive to negative to positive to negative, and that causes a current to flow between the live wire and the neutral wire. But in a normal operation of the plug, we do not expect anything to happen except current flowing between those two wires. In normal operation, there is no need for anything apart from live and neutral. They do the work. Now, if by some chance the current gets too big, the fuse steps into play. And all a fuse is two metal terminals with a very, very thin wire in the middle, inside a tube. And when the current through a fuse gets too big, you know that as currents go through wires, they'll get hot. And as this fuse wire gets really hot, if this current gets too big, it will break. And we can rate fuses, 3 amps, 5 amps, 13 amps, and that tells us the largest current that they will handle. So if I had a device that requires 3.2 amps of current, I would give a 5 amp fuse. It's the next one up. It's the fuse that will allow through the current it needs, but will stop it if that current starts to get excessive. So fuses are really important safety devices. There's one other really important safety device in this plug, and that is this green and yellow wire that goes to the third pin in the middle. Now this is the earth wire. Now the earth wire, in an ideal world, never gets used. We don't really want to use the earth wire because if it's being used, it means something's gone wrong. If I have something made of metal, let's imagine a toaster, primarily because it's one of the few things I can draw. So there's a toaster. I've got a lovely shiny metal toaster. There we are. Now this metal toaster, because it's got a metal case, if there's some fault inside and the live wire touches the case, so if I draw this cable, and if for some unknown reason the live wire manages to connect itself to that metal case, then of course if I touched the metal case, I'd be at risk of electric shock. That current from the live wire could flow through me instead of through the toaster, and apart from the fact that that would mean my crumpets were untoasted, I would end up with a nasty shock. The way to avoid that is that we connect the earth wire to the metal case. And this means if, in the unlikely event of a fault, the case becomes live by connecting to the live wire, the current won't flow through any user, but instead it will flow down the earth wire. Extra convenient is that that will give a really big current, which will almost certainly blow the fuse. So the earth wire and the fuse together act as protection against a fault. So any kind of fault on something with a metal case will require an earth wire to protect the user.